Hi everyone, welcome to this video, and we'll be going over a system response calculation in MATLAB using Simulink with building blocks. So here is the given system that we are going to build in MATLAB. This is a closed loop system with different transfer functions, and we will see that it's a second order closed loop system. Using building blocks of the Simulink, you will find the system response to different inputs. So let's dive into the building this closed loop system using the Simulink. So we'll start with clicking on the Simulink bottom, the top row. It'll open up a window that asks us about which type of the model we're interested in, so we can create a blank model. And I'm trying to actually hold the picture of the system on the right so that actually we can follow that. As you can see, we have a blank canvas and we can import our blocks using this library browser at the top. Over here, we have different blocks. As you can see here, let's start from the leftmost one, which is a step function. So we can easily type the step and hit enter, and it can bring us several options that you can choose from. Some of them are from the Simulink, some of them are from computer vision toolbox, and so on and so forth. Most of the items that we're interested in can be found in Simulink as well. So we have this step transfer function that we can easily drag and drop here. Let's move forward to the next block of the gain. So again, similarly, we need to type gain and hit enter. Again, in the Simulink, we have the gain that we can drag and drop. Then we have this error detector block that it is called as a sum. So if you press sum, we have an item for that is shown here with this, and apparently it doesn't look exactly the same as this one, but we can modify this later, and we'll get that done in a sec. Let's move forward with this next block, which is an integrator, but an integrator is essentially as a specific type of transfer function. So for a transfer function, we can write FCN, and it can bring us the transfer function. It's FCN that you can drag and drop here. We can modify that later. We have two of them, so I can copy and paste. So we have two transfer functions. Then we have another gain 1 and gain 2 at the bottom as well, so that we can make reuse of this gain again with another copy and another copying. And since this gain block is going to be towards the left in general, we need to flip that, and flipping is with Control I. If you hold on one of these blocks and hit Control I, it flips automatically. Then we have this mux block over there that combines all of the inputs and outputs that to the scope. So for the mux, we can typically write MUX. And we have this mux block over here that we can modify that and increase its number. So moving forward at the bottom, at the very bottom left, we have another transfer function. So again, we can copy and paste this transfer function here and put it down. Now we have the next building blocks are derivatives. So for derivation, we can simply write derivative, and you can see that the derivative blocks are here. We need two of them, so copy and paste two of them, and again another mux at the bottom, so we can actually copy this mux here as well. Then we have scope at the very right, so again we can write scope at the library browser. So the first one is also giving us the scope. Now we are almost done actually on all of the components that we're interested in. Now it's the time to connect them. And when you're hovering over each one of the blocks, on one edge of the block that there is an arrow, it can start connecting, and you can actually drag and connect to any adjacent block or the next block that you're interested in. So I'm trying to connect these blocks as follows. In the summation box, we have plus and negative and negative. However, in the original case, we have only plus and plus. So in order to edit that, we just double click on that. And at the bottom of the list of signs, we have plus plus. So we just need to remove one of the pluses and replace that with two negative signs and apply. And upon applying, you can see that this sum has changed into a system block that we were interested in. So that is how this summation block works. Now, in terms of the transfer function, we are interested in 1 over s. However, it is only 1 over s plus 1, so we need to modify that as well. We just double click on that, and numerator doesn't have to change. Denominator has to change indeed. It essentially has two values in this coefficient. The first one stands for the coefficient for s. The second one stands for the coefficient for s to the power of 0, or the constant number. And since the constant number in this case is 0, we need to remove the second one and replace that with 0. And once it's applied, you can see that it turns into 1 over s, which is our transfer function of the integrator. We can again double click on the name at the bottom and start writing integrator to make it very similar to the desired building block. Again, let's make change for the denominator coefficient here to make another transfer function as the integrator, and let's rename that to integrator 1. We can also reduce the size as we want and make them closer. Okay, now we have to connect the gain blocks. So this gain 1 block, let's call that as gain 1 as well. Gain 1. And this is gain 2. So if this output of the gain 1 is going to be entered to one of these negative signs, and the next one also is going to be entered, this it will be just like that. The input of these gain blocks is from the output of the first integrator. In order to make a connection, we can start from this arrow and bring it all the way to make such a connection to this line. And similarly, from this arrow, we can bring it all the way to this connection. Also, the line between the error detector and the integrator can be simply connected like that. And now we have the mux on the top right, which has 4 inputs. And in order to make this mux with 4 inputs, we just need to double click on that, and it says number of inputs. So we can press 4. It turns into a 4 input structure, and we can further zoom in and expand its size as well for better connections. Now, the outputs are going to be connected from here, as well as the output of the first integrator, the output of the error detector, as well as the step input. So we can make the connections just like that. And the output of this mux is going to be connected to the scope. So the connection for this scope is going to be through these 2 arrows from the top mux. And also, there is another actually connection needed from the bottom mux to the scope that we can actually simply drag and bring it closer to the scope, and it automatically turns into the second input for the scope. So it will be as simple as that. So let's start working with the bottom left transfer functions and derivatives. The transfer function is going to be filled with coefficients that are now m, b, and k. And we'll show actually how we would use them in a MATLAB.m file that we have also shown it in a previous video that you can watch in detail to see that how we can combine the .m file with Simulink, and we'll show it here again. So when we double click on that, we need to modify the denominator with the coefficients of m and b and k that will show where they will show up. So that is the transfer function that we want to have, and then there is a derivative, and that there is a second derivative that are all going to be connected to the next mux at the bottom right. This mux also gets 4 inputs, so we need to double click on that and change the number of inputs from 2 to 4. Okay, and get closer and expand its size to have a better connection. The first one gets all the way from the very beginning step input. So we get the first connection from here. We can further modify this with just moving the line a little bit to the left, and we can align them later. Then the second input is going to be from the second derivative. The third input is going to be output of the first derivative. Is like this. And the final one is going to be the output of the transfer function. So let's just simplify this a little bit, have a better view. Now, the transfer function and also this derivative are going to be connected as well. And this transfer function is fed with this input. So I'm going to actually move all of them a little bit to the right side. And also these two are also going to be connected. So with that, we have all of our connections set up. We just need to label all of these connections as well. We can double click on a line and write down the name that we want. Over here, we have x2, for instance. So we can start writing x2 on this one, x2 dot, because that's the derivative of x2, and over here, x2 dot dot, showing that that's the second derivative of x2. Essentially, this is the total transfer function that is going to be derived by two orders. Now, at the top also, we have different inputs to this mux that we can call them as f, as the step function or the input value, and then we have x dot dot. This third one is going to be x dot, and the last one is going to be x. Since this is an integrator, it essentially integrates x dot to result in x. Or in other words, if x is going to be reversed and this path is going to be derived, and there will be an x dot over here. So essentially, this system is showing the results of two systems, one at the top and one at the bottom, and we will show that how these two systems are correlated with each other. Now, the only thing is that we have a system with different coefficients at the bottom that we haven't defined that yet. But in order to do that, we need to start creating a .m file that holds all of those values in itself. And in order to do that, we will start creating a .m file. And in that case, we start with going to the top left menu, and there is a new button called the script. In this script, we can write down the coefficients of m, that is, for instance, 2, and we can give it a description of mass of a function or a system, for instance. B is going to be, for instance, 0.7, and this is the damper factor, and k is also 1 as a nominal value, that's the spring constant. So we can annotate all of these with some descriptive information. Now we need to save this function at a location that would be the same location of the Simulink model. So let's save this. And over here, I'm saving this function as Simulink variables. This is going to be a .m file, as you can see here. Save. The location for this is going to be within the documents folder. Now, in order to make MATLAB understood that it needs to follow the same position and at the same location, we have to save this file at the same location as well. So let's save this file as Simulink itself, or model at the same location. Now that we are done with the building of this matlab.m file, we need to recall that in our Simulink. In order to do that, we need to go to modeling at the top row, and then there is a model settings. We'll open that, and then there is a model properties. When we hit this, there is an icon for callbacks, and over here we need to enter the name of the .m file in this callback. That .m file can be found here as well, as you can see here. So the name is Simulink underline variables. We'll copy this, apply, and paste it at init fcn as well. Paste that, and then hit apply and OK. So in that case, the Simulink file will understand where to get those values. Now we're ready actually to run the file. There is a run button at the top row that we can hit and wait for the results to appear. So fortunately, the model has worked out successfully. It has grabbed all of the values of those variables within this transfer function from the .m file, and it has generated the results in the scope. So we need to just double click on the scope to be able to see the results. And over here, you can see that there are different outputs with respect to the model that we have. But in order to see which is which, we need to annotate that. And in order to do that, we need to go to View, and we have to check the legend of, so that all of those values of the inputs, f, or the x dot dot, or the x dot, and all of the other variables that we have annotated are also shown here. So essentially, we can see the system response towards a given step input. For instance, if the input is given with a step which is shown with this violet color, then x dot dot, x2 dot dot is going to be shown with this light blue, and x2 dot is going to be shown with this purple color, and x2 is shown with this yellow color as well. That's the output of the system. Okay, so if you want to change the output of the system with respect to different parameters of m, b, and k, we need to just modify the .m file, the MATLAB script that we had started our discussion with, as you can see on the left side, and it will be automatically applied to our building block and the system. In order to do that, let's try to change some of the variables. Say m from 2 needs to change to 5. We need to first save this .m file and then try to recall that with just running the model at the top right. And now we can see that the response in the time domain is going to be shown at the bottom right with the time that is not fitting in our scope. So this top time at the top right can be expanded a little bit to probably 40 and then run it again. That would give us enough time in the time frame so that we can have our results at the bottom finger. And with this, we can see that how different parameters of M, B, and K can affect the system response differently in terms of the overshoot value or the settling time, and all of those parameters that are important in calculation of this step response time, or the number of the oscillations that needs to be spent to settle the result. So this is how a given system building block is going to be analyzed and simulated in MATLAB, and the parameterized m.m file can be modified and coupled to the Simulink file so that we can run the Simulink model with a given parameters using another file. So you can start working on this model with changing different parameters and finding out what would be the step response of the system and how they would look like. So that was for today. If you like this video, please hit like and subscribe to the channel to view more of such videos in the upcoming days. Have a good one.